Okay, let's continue. So now I'm going to prove the theorem. Theorem is let fx be any continuous function on the segment AB. Then for any epsilon there exists f epsilon of x in C infinity from A to B such that model fx minus f epsilon of x less than epsilon for any x in AB. So this is the theorem which I am going to prove. Now, the proof is almost straightforward. First of all, to prepare, let us be the function f of x. I want to continue it outside the segment AB a little bit. Now say here it is f of A and here it is constant f of B. Yeah, so that the function is defined a little bit outside the segment AB. Now I define the following functions. I define the function phi delta of x equal 1 over delta phi of x divided by delta. So what is this? This is the function phi of x. Delta is some constant, positive. No, we are interested when it is less than 1. Now, this phi of x over delta, so we compress this function so that it is 0 outside the segment minus delta to delta, and this is that we expand it in the vertical direction in the same proportion. So this function will be like this. Yeah? And the result is the following, that this function phi delta in C infinity, phi delta of x is 0 for model x more equal than delta. Yes, phi delta of x more equal than 0, and integral, say, from minus infinity to plus infinity, phi delta of x dx equals 1. So it is another function of the same sort, but if this function looks like this, when delta goes to 0, it becomes higher and higher and more, narrower and narrower, and looks more like a needle than like a hill. And I define the following function: f delta of x equals integral f of y phi delta of x minus y dy. So for any x, we define this function. So what it is? It is, say, y-axis. Here is our function. It's a, it is b. No, the function is a little bit continued here and here, so that we could define it near the point a and b. So if x is here, then integral, no, let me this time, x minus y should be less than delta, otherwise this is 0. So it is from x minus delta to x plus delta. So we consider the point x here, x minus delta, x plus delta, and here is the function phi of x minus y, phi delta. It is the graph of this function. And we just define the function f delta as this integral. Okay, so we have to prove two things. We have to prove that this function, first, f delta of x is in C infinity as a function of x. Yeah. Now, how can we see it from this definition? First, we have to prove that this function is continuous as a function of x. F delta of x is continuous. And to prove that it is continuous, we have to find the difference between the values of this function at two nearby points. So f delta of x1 minus f delta of x2 equals integral f of y phi delta x1 minus y dy minus integral f of y phi delta of x2 minus y dy. No, I don't write the limits. If you wish, you can write so minus infinity to plus infinity. Because anyway, this function is 0 far from the point x1 or correspondingly x2. Okay, let us bring it under one integral. F of y phi delta of x1 minus y minus phi delta of x2 minus y dy. Now I have to invoke some properties of the function f. If f of x in C continuous function from A to B, then there exists some constant C such that module f of x less than C on AB. So the function is bounded. So continuous function on a closed interval is bounded. It is not true for any continuous function on open interval, but for closed interval it is true. Yes, and so let us continue with this. Module f delta of x1 minus f delta of x2 less or equal, so I substitute this fy by this c. Integral from minus infinity to plus infinity, module phi delta x1 minus y minus phi delta of x2 minus y dy. Now let me draw a picture. It is x1 and this is nearby point x2. So it is a little exaggerated. Phi delta x1 minus y, it is the y-axis. This is the summit. This is the summit, it is phi delta of x2 minus y. So this point is x1 minus delta. This point is x2 minus delta. This point is x1 plus delta, and this point is x2 plus delta. Yeah, and outside of these points, the difference, both functions are zero, so we can integrate from x1 minus delta to x2 plus delta. No, I assume that x1 less than x2. Now the function phi delta is a differentiable function. Yes, it is smooth function, so it has some derivative, and this derivative is bounded. Yes, so this means that phi delta of x1 minus y minus phi delta x2 minus y equals phi phi delta prime of some point theta. Theta is a point between x1 minus 1 and x2 minus y times the difference. Difference is, let me write module times module x2 minus x1. Yeah. Now the function is differentiable, so derivative is bounded because it is a continuous function derivative, and so less or equal than c1 module x2 minus x1. And so if you substitute it here, we have module f delta of x1 minus f delta of x2 less than c times the length of this interval x2 plus delta minus x1 plus delta. It is x2 minus x1 plus 2 delta times c1 and equal less or equal c prime x2 minus x1. Oh, one moment. It is the length of interval. It is c1 x2 minus x1 equals c prime x2 minus x1. Yeah. So we have this estimate, then this function is bounded, this difference is less than something proportional to x2 minus x1, so it goes to 0 as x2 minus x1 goes to 0. So this function is, first of all, continuous. Okay, now it is proved that this function is continuous. Now, what about differentiability? So, f delta prime of x equals d dx integral f of y phi delta x minus y dy. I have to differentiate with respect to x. So integral, okay, say again, from minus infinity to plus infinity, but in fact it is over the segment where the function is different from 0. So if you want to differentiate integral where the function which is under the integrand, this function, which is called integrand. function being integrated is called integrand. I like this word because it is a good word. It is integral dx. We have to differentiate with respect to x. F of y phi delta of x minus y dy equals integral. If you differentiate this does not depend on x. F of y dx phi delta x minus y dy equals phi delta is a differentiable function. In fact, it is infinitely many times differentiable. So I write it as integral f of y phi delta prime of x minus y dy. Now, this function phi delta prime is also a smooth function having which is zero outside some finite interval. So this means if x is changing, then by the same reason as it was for the function phi delta, this function is also a continuous function. Yes? AB. So we prove, and similarly we prove that f delta double prime of x I continue equals integral f of y phi delta double prime of x minus y dy, yes, and as a function of x, it is also continuous function, and so on. Fn of x delta also in C. For any n. So this proves that the function f delta is infinitely many times differentiable. Now it remains to prove that this function really approximates the function f. Prove that f delta of x goes to f of x as delta goes to 0. We have to prove this. To this end, I have to recall one other theorem of analysis. If fx is a continuous function on the closed segment AB, then fx is uniformly continuous. Uniformly continuous. What does it mean? For any epsilon, there exists delta such that if x1 and x2 are points on AB, and module x1 minus x2 less than delta, then module f of x1 minus f of x2 less than epsilon. This is the definition of uniformly continuous function. It is a bit stronger than the function which is continuous at every point. Yes? Now let's consider example. If you consider function g of x equal sine 1 over x, x positive, say between 0 and 1, but 0 is not included this endpoint 0 because the function is not defined there. So this function looks like this. It is oscillating and performs infinitely many oscillations as between -1 and 1 as we are approaching 0. So this function is continuous at every point, yes, but not uniformly continuous because here the wavelength, no distance between two, say, maxima goes to 0, and so we can, given arbitrary delta, we can find here interval close to 0, such that on this interval we have several, more than one such oscillations. So on this interval we can find 2 points where the difference is equal to 2, for example. We take point of maximum and next minimum, because here we have the distance between maxima and neighboring maxima, or maxima and next minimum, go to 0. We have this, I would say, condensation of these oscillations. So this means that this function is not uniformly continuous, does not satisfy this. So if you give epsilon equal, say, 1/2, then you cannot find delta which is good everywhere, because near 0 the oscillations become so close to one another, so dense that we'll have on arbitrarily small segment we can have, if it's close to 0, several maxima and minima. That's it. It was example. And the crucial thing here is that we have to consider closed interval, closed segment, so that it includes both endpoints A and B, and the function is continuous on this closed segment. And now our function f, first of all, is uniformly continuous. Now Let me write it. So fx is uniformly continuous on the segment AB. It is uniformly continuous. Now fix epsilon and let delta, depending on this epsilon, be such that in this definition, if x1 and x2 in AB and module x1 minus x2 less than delta, then module f of x1 minus f of x2 less than epsilon. So this theorem guarantees that such positive delta exists. And now let us consider the difference. The difference module f x minus f delta of x equals module fx minus integral say x minus delta to x plus delta f of y phi delta x minus y dy. Now fx is, we can put it in this integral and write it the following form. Integral from x minus delta to x plus delta fx minus fy phi delta x minus y dy. Simply because integral fx is constant in this integration, integral phi delta equals 1. Yes, so integral fx times phi delta equals fx. So we can, instead of putting it outside of integral, we can insert it inside integral. Now, y is between x minus delta and x plus delta. This means that module y minus x less than delta here. Yes? And so we can use this. So module fx minus f delta x is this less than module of this less or equal than integral x minus delta x plus delta epsilon times phi delta of x minus y dy. Integral of this integral is 1 of phi delta x minus y. So remains epsilon, equals epsilon. So if you move here fx minus f delta x and go along all this chain is less than epsilon. Yes? So if x, if delta is what is written here, let me draw a picture. So this is a graph of the function f. I take this point x. So we can find, okay, a segment, no, it is this short segment around x, such that in this segment, which is delta, so it is x minus delta, this is x plus delta, and this is fx plus epsilon, fx minus epsilon. So on this small interval, which is hardly seen here, the function f changes between fx minus epsilon and fx plus epsilon. Now we put here, let me a little bit draw in more detail, like here. So it is x minus delta, x plus delta. Here the function f changes within epsilon. So it is fx plus epsilon, fx minus epsilon, it is this. And now we multiply this by the function phi delta of x minus y. Yes? Multiplied by this function. This function is concentrated on this small segment, and its integral is 1. Yes, and on this segment we consider the function fx like fy on this segment, like fx plus difference, what is written here. Fx plus this difference, and this difference less than delta. Here is this difference, all within this narrow strip of width 2 epsilon. No, okay, so we integrate this small function with this weight. Yes, and the integral is less than epsilon. That's it. So we proved that for any epsilon there exists delta such that fx minus f delta of x less than epsilon. This is exactly what I wanted to prove. Now let me give the last stroke and we'll finish today. Suppose u of xt equals v of x plus t plus w of x minus t, where v and w are merely continuous functions. So how to approximate this function by a smooth function? Consider the function v delta of x equals integral v of y phi delta of x minus y dy, and w delta of x equals integral wy phi delta of x minus y dy. Then v delta w delta are in C infinity, and v delta minus v less than epsilon, w delta minus w, v delta of x, v of x, w delta of x minus w of x less than epsilon, on the segment AB. So we first choose any segment AB, then if delta less than delta of epsilon, delta of epsilon is some function which goes to 0 together with epsilon if v and w are continuous functions. Yes? And now we have the following. Define u delta of xt equals v delta of x plus t plus w delta of x minus t. Yeah? Then u of xt minus u delta of xt, u is here, less than 2 epsilon. Yes, because here they separately are less than epsilon, so maximum what is can be here, it is 2 epsilon. And u delta xt is a classical smooth solution of equation u delta ct minus u delta xx equals 0. It is smooth, and if you substitute it into equation, we get 0. That's it. So we restored, I would say, the honor of this solution. So this means that this function can be approximated by smooth function u delta, which is solution of the string equation, approximate with arbitrary accuracy. This means that hence u of xt is a weak solution of equation 1. This is what I was going to prove today. Next time we continue study of string equation. There is something to say more about this. For now, let's finish. Hope you are not completely exhausted. Have a good time. Bye.